for the introduction, this project is be made to design a virtual instrumentation system to collect data from a transducer and analyze the data in time and frequency domain by applying the Z-Lab software. In this project, a hairdryer will be used to create the sound wave. The laptop's microphone will capture the sound wave, which will then be evaluated and processed using the Z-Lab software. So basically, this setup will demonstrate the integration of hardware and software to capture the real-time data acquisition and signal processing. So this will highlight the virtual instrumentation applications such as like noise analysis, system diagnostic, and acoustic testing. So this is the simplest way, but it's also effective to do for a complex of a signal evaluation.
Assalamualaikum warahmatullahi wabarakatuh, and good morning everyone. Today I will briefly explain the principle of operation, industry application, and the complete sensor system of a microphone. So first, the principle of operation. A microphone works by converting sound wave into electrical signal. It detects a variation in acoustic pressure and translate them into the corresponding voltage chain, and enabling sound to be captured and processed. So next, in terms of industrial application, microphones are widely used for noise monitoring, communication system, and quality control process. For example, in manufacturing, they have a monitor machine sound, allowing for early detection and abnormalities or potential failure. So finally, in a complete sense system, in the microphone act as the primary sensing element, complemented by a prime failure for strength weak signal and a data system to digitalize this signal for future processing and analysis. So this element make a microphone indispensable in various technology and in industrial. So this concept all three in the singles in this slide. Thank you.
Assalamualaikum. My name is Wan Muhammad Zafran bin Wan Zailani. My metric ID is MA22146. I will present about theoretical background on vibration or acoustic using microphone. Microphones are essential device used in vibration and acoustic measurement to capture sound or vibration signals and converting them into electrical signals for analysis. Acoustics is the study of mechanical waves that propagate through a medium such as air, water, or solids. These waves are characterized by parameters such as frequency, amplitude, and sound pressure. The frequency of a sound wave, measured in Hz, determines its pitch, while its amplitude reflects the wave energy and is associated with the loudness. And the pressure variation caused by sound wave, known as sound pressure, are typically measured in Pascal. In this project, the microphone acts as a transducer, converting sound wave into electrical signals for analysis. Using techniques like fast Fourier transform, we analyze the sound in both time and frequency domains to identify key characteristics like dominant frequency and sound levels. We use the decibel scale, a logarithmic measure, to quantify the hairdryer loudness. Proper calibration and minimizing environmental noise were essential to ensure accurate measurements. By controlling factors like microphone placement and reducing interference, we achieve reliable data, highlighting the importance of precision in acoustic analysis. Acoustic measurement often use the decibel scale, a logarithmic representation of sound intensity. And the sound pressure level SPL in dB is calculated using the formula SPL equals to 20 log P over P ref.
Hi everyone, my name is Alfred Paul. Anak lelaki Arokia, my matrix number is MA24040. Now I will be explaining about the experimental setup. First of all, I will be explaining about the apparatus and software needed to conduct this experiment. First, we will be needing a laptop. The laptop will be acting as a host for the Daisy Lab software, which is used to record the sound, create and manage modules for acquiring, processing and analyzing data. Second item we'll be needing is the hairdryer. The hairdryer will act as the sound source for the experiment. Next, we'll be using a software called Daisy Lab. Daisy Lab is used to get the results of the time domain graph and frequency domain graph. Next, we will be using Decibel X. Decibel X will be used to measure the average decibel value of the sound source. Next, I will be explaining about the hardware setup and Daisy Lab layout. First image shows that hardware is set up with Daisy Lab software and with the help of Decibel X application on the side. The next image shows a clear Daisy Lab setup layout. To acquire this setup layout, firstly we will be going to the modules at the toolbar, then click inputs/output, and to open the driver, we will be clicking on the analog input and drag it to the workspace. Next step will be going to the display and click on the digital meter and place it next to the analog input and connect it. Then click on the display window to see the digital meter and test the circuit by running the Daisy Lab. For this, we will be switching on the hairdryer to see the reading on the digital meter. Next step will be click on the mathematics and insert the formula interpreter right next to the digital meter. The following step will be insert another digital meter next to the formula interpreter. Another upcoming step is we will open the files and insert the write data in the workspace. The purpose of the write data module in Daisy Lab is to save collected and process data to file for further analysis, reporting or documentation. Following by that, we will navigate to modules and click display and select Y/T chart module to measure the time frequency domain. Next, we will navigate to modules, click signal analysis and then choose the data window. The data window in Daisy Lab is a feature used to define and manage the portion of the data stream that is processed, displayed or analyzed at a given time. Next, we have to attach a FFT fast Fourier transform window next to the data window to minimize spectral leakage and improve the accuracy of the frequency domain analysis. Lastly, we will be inserting another YT chart to show the frequency domain, and we will be connecting all the modules together. Next is the procedures of measuring that was done in this experiment. Firstly, it was done without formula. For the steps that need to be taken for procedures of measuring without formula is we have to get ready with the hairdryer, Daisy Lab software on laptop and the Decibel X app on the smartphone. Make sure there is no noise interpretation. Next, we'll be switching on the hairdryer and place it nearby the laptop and smartphone. We'll be running the Daisy Lab and start the Decibel X simultaneously for 30 seconds to obtain a steady and accurate data. After 30 seconds, the VRMS value from the digital meter Daisy Lab and the average dB value from the sound meter Decibel X are obtained as shown in the diagram below. Insert the values in the formula to obtain the value of V reference. That will be the last step taken for without the formula. Next, procedures of measuring with the formula. We have to get ready with the hairdryer and Daisy Lab software on laptop. For this, we won't be needing the Decibel X app on the smartphone. Next, we will be inserting the formula 20 log n 0 over 0.001346 into the formula interpreter in the Daisy Lab. Make sure there is no noise interpretation as well. We will be switching on the hairdryer and place it nearby the laptop. Then we will be running the Daisy Lab for 30 seconds to obtain a steady and accurate data. After 30 seconds, the decibel value from the digital meter Daisy Lab is obtained as shown in the diagram.
A very good day, my name is Mavindran Anarki Shashindran and my matrix number is MA24027. Alright, so for today we are going to talk about the discussion that we have done. Alright, as you can see over there, it's the time domain graph. The graph shows the reading of the voltage with time between negative 5.0 volt to 5.0 volt and the peak value was at 3.5 volt by referring to the graph. Next, the frequency domain graph. It illustrates that the highest peak had occurred at 450 Hz. A sudden spike in the frequency domain graph is due to external noise or interference picked up by the sensor during the measurement. Following that, as you can see over here, the VRMS and the decibel value that was obtained from the DAISY lab. The average sound level for the hairdryer is 80.9 dB according to the sound meter application and 80.86 dB according to the DAISY lab. So the percentage error is around 0.05%. However, it is recommended to choose the value from the DAISY lab app as it is more accurate compared to the sound meter application, which is Decibel X. The decibel value obtained using DAISY lab is generally more accurate than the value measured with the Decibel X app due to the differences in hardware precision, software customization, and environmental control. DAISY lab setups typically involve high-quality, calibrated microphones and professional-grade hardware interfaces. These tools are specifically designed for precise voltage readings and reliable sound measurements, ensuring that the data collected is highly accurate. In contrast, Decibel X relies on the built-in microphone of smartphone, which varies significantly in quality and is not optimized for accurate dB measurements. Additionally, smartphone microphone is often uncalibrated, leading to potential errors. As for the conclusion, this project successfully demonstrated the design and the implementation of a virtual instrumentation system to measure and analyze the vibration frequency and sound intensity of a hairdryer. Using a microphone as a sensor, the collected data was processed and analyzed in both time and frequency domains with the DAISY lab software. The experiment effectively illustrated the utility of signal processing techniques such as FFT to identify key parameters like peak frequency and decibel levels. The result indicated an average sound level of approximately 80.86 dB with minimal error when compared to value obtained using a smartphone application. This highlights the higher precision and reliability of professional-grade setups over consumer-grade tools. Additionally, the experiment emphasized the importance of controlled environments and proper calibration in achieving accurate acoustic measurements. The project objectives were met, showcasing the effective integration and theoretical knowledge and practical application in acoustic analysis.